Hello, welcome back again to ELEC 861. We are covering chapter 1, which is basics of probability theory. So we want to give you a new meaning. This is a standard meaning of probability mathematics. It is based on probability theory. So we will introduce probability space. This chapter is a bit theoretical and is just an exposure, so don't be scared. So probability theory is based on probability spaces, which a probability space has three elements. You need to have a sigma algebra and you need to have a probability space. Probability measure. So sigma algebra is defined on any set. We'll learn about these. Then we will talk about conditional probability and different events. So you have learned in your undergraduate course several meanings of probability, which are different interpretation. They are not mathematically solid, so they are meant for ordinary people or people who want to learn a little bit of probability theory to use it in some engineering application. But if you want to use it in much more in-depth applications and is solid background, you need to have a bit more. And you can learn. So in this chapter, we will quickly introduce a mathematical foundation of probability theory. It doesn't mean that all of the course needs this one. Some portion of the course, particularly one of the small chapters, need this one a bit more in depth for the convergence and stochastic calculus and so on, which is not as important. So the next chapters are more practical than this one. This is a bit theoretical, so I don't want you to be scared. So we have to now introduce probability space. A probability space is a triplets. So it has three components. Sigma sample of possible set of possible outcomes, then a sigma algebra over it, and then a probability measure. So let's see what is the exact definition. So probability space is a triplets. It has three components: a set, a sigma algebra over L, and a probability measure. So see what are these ones. So these L could be any set. It could be possible outcomes of a coin experiment, which is head or tail, or it could be possible outcomes of a dice experiment, 1, 2, 3, 4, 5 and 6, or it could be time instance that your car will fail to operate well, which is the set of real numbers. And then we need a sigma algebra, so we'll give a specific definition for sigma algebra. Then we want to define a probability measure. We say a probability measure is a countably additive probability measure on L and F, and this is this is a probability space. So we need to define these two components, sigma algebra and countably additive probability measure. So we need to learn it and a little bit of exercise, and we are on right track. So sigma algebra is a collection of subsets of L. So F, we call it sigma algebra. If it is a collection of subsets of L, if there are some conditions which are satisfied. The first condition is that L itself should be inside sigma algebra, and for any member of F, its complement should be also inside F. Particularly here, because we know that L is in F, L is inside your sigma algebra, and then because of the second condition, so complement of these should be in L. So complement of L should be also in sigma algebra, and this is just nothing more than empty set. So from the two property, we conclude that the whole set and empty set are inside the sigma algebra. Members of a sigma algebra, we call them an event. The third and last required property for a sigma algebra is that if your sigma algebra, if you take any two members, it should be closed to union operations. So if you have A and B, a union of them should be there. So any collection of subsets of L which satisfies these three properties, we call it a sigma algebra. Now, an example, a first example is if you experiment a coin experiment, or if you experiment everything else, the collection of all subsets of L. So the first sigma algebra is the collection of all, so that means that L itself, L bar, and anything else. For instance, if L has two members, one sigma algebra is a trivial sigma algebra which is useless for us, is that L is in there, its complement is there, and then you can verify that the condition 1, 2, and 3 are satisfied. But this is not useful for us because in that case we could define only probability of these and these. This probability we'll see that is 0, this is 1, and nothing else. The second sigma algebra that we could define on a set with two elements is that F contains empty, its complement here, and it contains A, and it contains this complement of that, this is this. In that case, this is denoted by 2 to the power of L, or the set of all subsets of L. This is called power set. Power set is the set of all subsets of L. So the collection of all subsets of L is called power set. So this is the smallest sigma algebra. This is the smallest sigma algebra, which is not useful. This is the largest one, which is useful in probability theory, but sometimes it has elements that we may not be able to handle in probability. So we'll learn a little bit about that more. So the simplest useful sigma algebra is the subset of all for the set of real numbers. We could have the set of all subset of real numbers, but we cannot measure its probability. This is why we define a useful sigma algebra, and we say that a sigma algebra, we call it Borelset. So Borelset for the set of real numbers is defined for if L is equal to set of real numbers. We define a Borelset. So this the collection of all subset of L which includes the interval. So like this Borel field, its entries A, if A is inside B, we could write A in terms of union of intervals. So it is like an interval like that, all the real numbers between A and B. So is equal to interval 1, union interval 2, etc. So you could write it in terms of a number of, it could be not countable, a number of intervals. So if you want to say that, so this is interval 1, I1, it could be interval line 2, etc. So Borel field is a sigma algebra, the smallest sigma algebra, which includes all of these ones. Obviously, because it should be a sigma algebra, it should include their union. It should include their intersection, because complement of union is intersection. So this is why we learned the sigma algebra and these things. Now, the last element is a probability measure that we will have lots of nomenclature for that. So let's say we have a sigma algebra over L, and we define a probability measure. So a probability measure is called countably additive probability measure if there are three properties. So in your undergrad course, perhaps you learn these as axioms. First of all, for any member of sigma algebra, probability is non-negative. So the first property of probability is non-negative. for all members of your sigma algebra. The second property is that probability of your whole set, probability of everything, probability of all possible outcomes is 1. So the total probability, so we call it the total is 1, not less than 1, not more than. And the third property is that if you have any two events, any two sets inside, both of them are inside your sigma algebra. This is a member of your sigma algebra. This is a member of your sigma algebra. Remember that if something is not inside your sigma algebra, we don't define the probability for it. So in that case, if they are disjoint, then probability of union is equal to the sum of probabilities. So this is called additivity property. If you have these three properties and the sigma algebra, we have a probability space. So we'll have some examples to learn it a little bit more. But for example, if these two guys are not disjoint, so let's say if A and B are like that, so this is A and this is B, and then here is A intersection B. Okay, in that case, you could measure probability of A union B. You could say that this is equal to, you could write it as, let's say, 3 parts. So let's say this is part 1, part 2, and part 3, okay? And say that these 3 parts are disjoint. So you could say the probability of part 1 plus probability of part 2, and then plus probability of part 3, okay? Now, part 1 and 3, so you could say that probability of A is equal to probability of part 1 plus probability of part 2, and you could say probability of B also is probability of part 2 plus probability of part, let's say, 3, okay? And then from here, you could conclude that probability of union, if they are not disjoint, is going to be probability of A plus probability of B, and then minus probability of A intersection B. And remember that part 2 is A intersection B. So this was just an example.